Hello, and welcome to this GCSE Physics exam preparation video. This is Electricity 2, Mains Electricity. Current electricity comes in two forms: alternating current, AC, and direct current, DC. Alternating current is where the current goes in both directions around the circuit. This type of electricity is found in mains electricity and anything that runs on mains electricity. Mains electricity in the UK is at 230 volts and 50 hertz, and these are two values that you need to remember. 50 hertz means that the current changes direction 50 times a second. Direct current, DC, this is where the current goes in one direction only. This type of electricity is found in anything that runs on batteries. You may need to recognise whether current is AC or DC from the graphs. Any graph that has the potential difference going in the positive and negative direction, regardless of the shape of the graph, is showing you an alternating current. Any graph that has the potential difference always on the positive side or always on the negative side, regardless of the shape of the line, is showing you a direct current. These two diagrams show the inside of the 3-pin plug. As you can see, there are two varieties. One has a 3-core cable, which has the neutral, the earth and the live wire, and the other is the 2-core cable, which only has the neutral and live wires. You need to be able to label the wiring inside of a plug, including some of the features like the cable grip, which is a safety measure. It grips that cable and makes sure the wires inside the plug do not come loose. You also need to know the colours of the 3 main wires and where they are wired into the plug. The live wire, this carries the alternating potential difference into the appliance. It has a voltage of 230 volts. Even if the appliance is switched off, the live wire can still be dangerous to touch because you could make a circuit between the live wire and the earth, and that would cause an electric shock. The neutral wire, this completes the circuit and has a voltage of 0 volts. The earth wire, this is a safety device. It's only needed if the appliance has a metal case, which is why you have the 2-core and the 3-core cables. If the case is plastic, a 2-core cable can be used, which doesn't have the earth wire. Usually the earth wire is at 0 volts. It's only used if there's a fault in the appliance that causes the metal case to become live. If the electricity then flows down the earth wire, this causes a surge in the current as the resistance of the earth wire is really low. This surge in current causes the fuse wire in the fuse to heat up, which will then melt and break. The circuit will be broken, no more electricity will flow, and this will make that metal casing safe. Power transferred in circuit components depends on the current through it and the potential difference across it. It can be calculated using the following equation, one which you need to learn. This is power equals the potential difference times the current. Power can also be calculated with a second equation, which again, this is one that you need to learn. And this is power equals the current squared times the resistance. Only the current is squared in this particular equation. Units, power, capital P, is in watts, capital W. Potential difference, capital V is the symbol, and the units are the volt, capital V. Current, the symbol for current is I, and the unit is the amp, capital A. Resistance is R, and the units are ohms, which is the Greek letter capital omega. Power calculations do come up quite a lot in your exams, so make sure that you know the power equations in this topic and the power equations in the energy topic. Many electrical appliances are designed to transfer energy from the battery or from the main supply into kinetic energy, if it's an electric motor, or to thermal energy in heating devices. Work is done in a circuit when the current flows, and the amount of energy transferred depends on the power of the device and the amount of time that the device is left on. These variables are related in the following equation. Energy equals the power times the time. You can also use charge and potential difference to calculate the energy transferred. Energy equals the charge times the potential difference. Units wise, energy, E, units is joules, capital J. Power, P, the unit is the watt, capital W. Time, lowercase t is its symbol, and the unit is seconds, lowercase s. Charge, its symbol is capital Q, and the unit is the coulomb, capital C. Potential difference, symbol V, has the unit of the volt, capital V. The national grid is a system of transformers, cables and pylons that transmits electricity from power stations, where the electricity is generated, to homes and businesses. Here we've got a diagram, we've got the power station here, and the electricity goes via a step-up transformer into the pylons, then to a step-down transformer and eventually into homes and businesses. Step-up transformers increase the voltage of the electrical supply. This allows the current to be low, so the resistance in the transmission line is reduced. As the resistance is low, there is less energy lost to the thermal store of the surroundings, and so the transmission is more efficient. Step-down transformers, they reduce the voltage of the supply before it gets to homes and businesses, and this is for the safety of the consumer. This diagram shows you what a step-up transformer consists of. So you have a primary coil on the input side and you have a secondary coil on the output side, and they are connected together by an iron core. A step-down transformer is more or less the same, the only difference being that in the step-down transformer, the primary side has more turns on the coil than the secondary side. In the step-up transformer, it's the opposite way around. As power is energy transferred every second, and energy has to be conserved, then the energy transferred each second on the primary side of the transformer, regardless of whether it's a step-up or step-down, should equal the energy transferred on the secondary side of the transformer. And this is assuming that the transformer is 100% efficient and none of the energy is lost to the thermal store in the surroundings. To calculate power in an electrical circuit, you need to use the following equation. P equals V times I. Power equals the potential difference times the current. So on the primary coil, you have power on the primary coil equals the potential difference on the primary coil times the current on the primary coil. And on the secondary coil, the output side, you have the power on the secondary coil equals the potential difference on the secondary coil times by the current on the secondary coil. Now, as the power on the primary must equal the power on the secondary, then we can put these two equations together to get a new expression. So power on the primary equals the power on the secondary, and that gives us this expression here, which is potential difference on the primary times the current on the primary equals potential difference on the secondary times current on the secondary. And this equation is given to you on the data sheet. You may have to use this equation in the exam, substitute in your numbers, and then rearrange for your unknown. You can then calculate your unknown, whatever that particular unknown might be. And that's it for this video. Thank you very much for listening.